Right now, while you're watching this, a small machine built almost 50 years ago is floating in a part of space no human has ever visited. It is 25 billion kilometers from Earth. It is drifting through a region scientists genuinely did not expect to find. Pressures are jumping, magnetic fields are spiking, and brand new scientific papers published this year are trying to explain what this old spacecraft is currently measuring. The sun it left behind is still shaping the medium it now sits inside. This is the hidden story of Voyager 1. Welcome back to Proof, where we uncover the hidden truths of the cosmos. If you are new here, hit subscribe right now, because what you are about to hear is genuinely new science. Not rumors, not clickbait, real peer-reviewed papers published in 2026 debating live data coming in from a place nothing on Earth can ever reach. Most people will never know this is happening. Drop a comment right now and tell me where you are watching from, because I rate everyone, and I want to know how far this story is traveling. So let us start with where Voyager 1 actually is right now, because location is everything in this story. Voyager 1 launched on September 5th, 1977, from Cape Canaveral, Florida. It flew past Jupiter in March 1979, then past Saturn in November 1980, and then it just kept going, outward, past the planets, past Pluto, out into the dark. On August 25th, 2012, at 121.7 astronomical units from the Sun, it crossed something called the heliopause. The heliopause is the outer edge of the Sun's magnetic bubble, the point where the solar wind finally gives way to the gas and dust and magnetic field of the space between the stars. The moment Voyager 1 crossed that line, it became the first human-made object to enter interstellar space, the very first thing we had ever built to leave our solar system. That was 13 years ago, and Voyager 1 has not stopped moving since. Right now, in 2026, it sits roughly 167 astronomical units from the Sun. That is about 25 billion kilometers from home. Its radio signal, traveling at the speed of light, takes over 23 hours to reach Earth. Think about that. Every instruction NASA sends to Voyager 1 takes 23 hours going out. Every bit of data Voyager 1 sends back takes another 23 hours coming home. The spacecraft is operating on a one-day round-trip delay, and it has been for a while. But here is the part that makes 2026 genuinely different. By November 18th, 2026, that travel time will reach exactly 24 hours. One full day. Voyager 1 will become the first human-made object to sit one light day from Earth. A signal sent right now would only just be arriving there. And a signal sent there right now would only just be arriving here. Here is where the story gets strange. Because the place Voyager 1 is currently drifting through is not what physicists expected to find when they built the spacecraft. The region was not in any textbook when Voyager 1 was designed in the 1970s. No one had measured it directly. No one had any way to. The interstellar medium, which is the name for the gas and dust and charged particles filling the space between stars, was modeled from a distance. Astronomers had studied it by looking at distant stars and seeing how their light was filtered through it. They had built up a picture of a relatively smooth, relatively calm environment with some turbulence and some density variation, but broadly predictable. The expectation was simple. Once Voyager crossed the heliopause and moved far enough away from the Sun's influence, the medium around it would start to settle down, become quieter, become more uniform, begin to match the calm, distant picture that telescopes had been showing for decades. That is what was supposed to happen. That is not what happened. What Voyager 1 actually found on the other side of the heliopause was a layered, surprising, deeply active environment. One that kept presenting new features as the spacecraft drifted deeper into it. Features that required new explanations. Features that are still generating live scientific debate in peer-reviewed journals in 2026. Scientists now have a name for the specific region Voyager 1 is moving through. They call it the Very Local Interstellar Medium, sometimes shortened to VLISM, the thin shell of interstellar space that immediately surrounds our solar system, distinct from the broader interstellar medium farther out. And the VLISM, it turns out, is one of the strangest places we have ever directly measured. To understand why this is so strange, we need to talk about what physicists thought the heliosphere, our sun's magnetic bubble, looked like before any spacecraft left it. For decades, the standard textbook picture was a smooth, comet-shaped bubble, a rounded nose on the side facing the direction the sun is moving through the galaxy, and a long streaming tail behind it, like a drop of dye being pushed through water. The heliopause, the outer skin of that bubble, was assumed to be a relatively sharp, well-defined surface. And the interstellar medium on the other side was assumed to be largely undisturbed once you got far enough beyond it for the sun's influence to fade away. The very local interstellar medium was thought of as a kind of waiting room, a buffer between us and the broader galaxy. Quiet, predictable, well-behaved. Voyager 1 has been systematically dismantling that picture since the moment it crossed the heliopause in 2012. The first surprise was the crossing itself. Instead of a single, sharp boundary, Voyager 1 found a transition. The magnetic field that the spacecraft was measuring did not immediately snap into the orientation it was expected to take. The particles around it changed, but not always in the ways the most detailed pre-crossing models had predicted. Ed Stone, who was the Voyager project scientist from before launch through much of the mission, said plainly at the time that the interstellar space Voyager 1 had entered was not what anyone had expected. Don Gurnett, presenting plasma wave data at a 2014 conference, said something even more direct. He said that most people would have thought the interstellar medium would be smooth and quiet. But the shocks and tsunamis Voyager was detecting were far more common than anyone had predicted. Those surprises continued through the years that followed. Between 2012 and 2022, Voyager 1 moved through a sequence of clearly named, clearly documented features in the VLISM. There were shocks, sharp compression waves in the plasma, the electrically charged gas between the stars that rang through the medium like a bell. There were pressure fronts, more gradual compressions that also produced jumps in both magnetic field strength and electron density. There was an outer heliosheath where the magnetic field was slowly rotating toward the direction a satellite called IBEX, the Interstellar Boundary Explorer, had measured remotely from inside the solar system. Each of these features had to be explained. Each of them, in its own way, did not fit the old textbook picture. Each of them told scientists that the VLISM was more structured, more eventful, and more physically rich than anyone had been able to see from the inside before. But none of those surprises prepared scientists for what happened in May of 2020. Right here is where the modern story really begins. In May 2020, at a position about 149.3 astronomical units from the Sun, Voyager 1's magnetometer registered a sudden large jump in the strength of the magnetic field around the spacecraft. The field strengthened by a factor of about 1.35 over a period of roughly 8 days. The proton density around the spacecraft rose by a similar factor at the same time. Scientists labeled this event the second pressure front. Earlier pressure front events had produced field jumps too, but usually temporary ones. The field would rise, then drift back to its previous level within a few months. That is not what happened this time. Instead, the field kept rising. It climbed steadily until it reached a peak of about 0.56 nanotesla in early 2021. Then it slowly declined to a stable elevated level of around 0.5 nanotesla. This sustained period of elevated magnetic field strength, lasting from approximately 2020.4 through 2022, while Voyager moved from about 149 astronomical units out to roughly 155 or 156, was given its own name, the magnetic hump. And the magnetic hump was not in any pre-existing model of the interstellar medium. Nobody had predicted it. A 2023 paper by Berlage and colleagues estimated that the magnetic hump was caused by elevated solar wind dynamic pressure and high speeds observed at Earth between roughly 2015 and 2017. These were compressions driven by the natural rise and fall of the Sun's 11-year activity cycle. They traveled outward through the solar system, hit the heliopause, and transmitted their energy deep into the interstellar medium on the other side. In other words, the Sun's own activity, more than 30 astronomical units beyond the edge of its magnetic bubble, was still shaping. The medium Voyager 1 was drifting through. The boundary was not a wall. It was behaving more like a membrane, transmitting pressure from one side to the other in ways that the old models had not fully captured. But then came the part that is confusing scientists right now, in 2026. After the magnetic hump faded around 2022, the region Voyager 1 moved and to behave differently from any region it had been in before. The post-hump region, the area beyond roughly 155 to 165 astronomical units, was quieter in a very specific way. And two major scientific papers published this year, both in the Astrophysical Journal, are still actively debating what that quiet actually means. Let me walk you through both papers because they are at the heart of what is happening right now. The first paper, published in 2026, was led by Federico Fraternale and Nikolai Pogorilov at the University of Alabama in Huntsville. Their team used sophisticated magnetohydrodynamic simulations, which means computer models that track how magnetic fields and plasma behave together as a fluid, driven by actual solar wind data, to reconstruct what should have happened at Voyager 1's location between 2020 and 2025. Their simulations convincingly reproduced the magnetic hump observations. They linked the hump specifically to solar cycle 24, the 11-year cycle of solar activity that peaked around 2014, and they predicted that similar magnetic field structures should occur once per solar cycle. They also predicted that Voyager 1 should start to feel effects related to solar cycle 25, the current cycle, in the coming years. So the hump, in their view, was not an accident. It was a predictable output of how the sun breathes. The second paper, published on May 20th of 2026, was led by Jiawoo Park and included colleagues along with Leonard Berlage, the same Berlage whose earlier work first described the magnetic hump. This paper covered Voyager 1 magnetic field observations from 2020 through the middle of 2025. And what they found was strange. In the region before the second pressure front, the magnetic field fluctuations were turbulent and non-Gaussian. Now, non-Gaussian is a statistical term. It means the fluctuations varied in ways that did not match the smooth bell curve pattern you would expect from a well-mixed random environment. They spiked and dropped irregularly. After the hump, that irregular behavior essentially vanished. The fluctuations became smooth, calm, and statistically Gaussian. The intermittency, the tendency for the field to spike unpredictably, was gone. And this is where the live scientific debate is happening. Because that shift from a noisy, spiky, irregular pattern to a smooth, calm, well-behaved one is genuinely puzzling. Some researchers initially interpreted the calm as a sign that Voyager 1 had finally crossed into something fundamentally new. That it had passed beyond the zone shaped by our own heliosphere and into truly undisturbed interstellar space. If true, that would mean our sun's influence on the surrounding medium extends much farther than previously thought. Perhaps all the way out to 165 astronomical units, instead of stopping at 121.7 where the heliopause sits. The Fraternale and Pogorelov paper argues against that interpretation. They ran the simulations and concluded that neither the turbulence observations nor their global models support the conclusion that Voyager 1 entered a fundamentally new region. Instead, in their view, the calm behavior in the post-hump region is a natural consequence of the way the magnetic hump event itself filtered out and dissipated the solar-driven disturbances that had been creating the earlier turbulence. The hump, in their model, acted like a kind of effective filter, a barrier that weakened the shocks in the merged interaction regions, which are big bundles of solar wind disturbances traveling outward from the sun before they could reach farther into the pristine interstellar medium beyond. So the calm is real, but it is not because Voyager 1 crossed into something new. It is because the hump used up the energy from the disturbances before they got there. That distinction matters enormously. If the calm means Voyager 1 has reached truly undisturbed interstellar space, the picture of our heliosphere and its reach has to be redrawn. If the calm is just a temporary filtering effect, then the medium beyond the hump is still fundamentally the VLISM, just in a quieter phase. Quieter, but eventually going to be stirred up again when the next round of solar-driven compressions from cycle 25 start arriving. Right now, in 2026, the scientific community does not have a final answer. What it does have are two strong, well-argued papers that disagree, both based on the same underlying data, both using different methods, both pointing toward different conclusions. That is what real, live, active science looks like. Now, let us talk about something almost as remarkable as the science itself. The engineering reality behind every measurement Voyager 1 sends home from the VLISM. Voyager 1's main radio transmitter produces about 22 watts of power. That is roughly the same as a refrigerator light bulb. By the time that signal has crossed 25 billion kilometers of interstellar space and arrived at Earth, it is billions of times weaker than when it left. The only reason NASA can pick it up at all is because of the Deep Space Network, a global system of enormous dish antennas in Goldstone, California, in Madrid, Spain, and in Canberra, Australia, the largest of which are 70 meters wide, among the most sensitive radio receivers ever built by humans. Even with those massive antennas, the data rate from Voyager 1 is only about 160 bits per second at most. 160 bits. That is roughly the size of a short text message every few seconds. Everything we know about the VLISM, every measurement behind the magnetic hump, every pressure front, every density map, all arriving at that trickle of a rate. One thin stream of data crossing 25 billion kilometers of space and landing in a desert dish in California. And here's the urgency. Voyager 1 is powered by 3 radioisotope thermoelectric generators, devices that convert heat from the steady decay of a radioactive element called plutonium-238 directly into electricity. These generators have been losing power at a rate of about 4 watts per year since launch. They now produce less than half of what they generated in 1977. To keep the spacecraft alive as long as possible, NASA engineers have been making careful decisions about which instruments to keep running and which to shut down. The cosmic ray subsystem was powered off in February 2025, and on April 17, 2026, NASA shut down the low-energy charged particles experiment, an instrument that had been operating continuously for 49 years. That is almost the entire mission. That instrument had been collecting data since before most of the people watching this video were born. The reason these shutdowns matter is that the team at NASA's Jet Propulsion Laboratory is preparing a carefully planned power management operation they have nicknamed the Big Bang. The idea is to shut off some lower priority power devices on the spacecraft while turning on alternative heaters and controllers that use less electricity, all in a coordinated sequence. And if it works, it could free up enough electrical headroom, meaning extra available power, to keep Voyager 1's remaining instruments alive into the 2030s. The Big Bang is being tested on Voyager 2 first, in May and June of 2026. If the test goes well, the team plans to attempt the same operation on Voyager 1 no earlier than July 2026. If the Big Bang works as intended, it could buy Voyager 1 several more years of life. The two instruments still operating on Voyager 1 right now, and the two instruments generating the data behind the 2026 papers, are the plasma wave system and the magnetometer. So the choices NASA engineers make right now, which instruments to keep running, which to power down, which to handle carefully for additional years, are not just engineering decisions. They are decisions about which new science gets to exist. They are deciding, in real time, whether humanity gets to keep reading new pages from this region of space, or whether the chapter closes. And that decision connects directly to a much newer mission: NASA's Interstellar Mapping and Acceleration Probe, IMAP. IMAP launched in September 2025 and is now operating near Earth at the first Lagrange point, a gravitationally stable parking spot about 1 million miles from Earth in the direction of the Sun. IMAP studies the boundaries of the heliosphere from the inside using energetic neutral atoms, particles that travel inward from the edges of our Sun's bubble without being deflected by magnetic fields. But to interpret what IMAP sees, scientists need to know the actual plasma density, magnetic field strength, and turbulence properties of the interstellar medium on the outside of those boundaries. The only place those measurements are coming from in 2026 is Voyager 1, sitting one light day away. So a 49-year-old spacecraft and a brand new 2025 mission are actively working as scientific partners across a distance of 25 billion kilometers. One looking from the inside, one sampling from the outside, both studying opposite sides of the same boundary. Now, this is where I want to zoom out for a second, because there is a deeper story underneath all of this. The VLISM is not just an abstract edge zone that scientists study out of curiosity. It is the region of space that shapes how our entire heliosphere interacts with the rest of the galaxy. Understanding it properly affects how we model cosmic ray shielding, the natural radiation protection our Sun's magnetic bubble provides for the inner solar system, including the planet we live on. It affects how we model the energetic neutral atom ribbon that IBEX and IMAP measure. It affects how we understand star systems in general interacting with their surrounding interstellar environments. Every new measurement from Voyager 1 feeds into models that scientists are actively using right now, not next decade, right now. And the extraordinary thing about this is when it is happening. The science is happening in live, real time, in 2026, driven by data from a spacecraft that should, by any reasonable engineering expectation, have gone silent years ago. Its plutonium is half gone. 4 of its 10 original science instruments have been deliberately powered down to keep the rest alive. Its signal, weaker than a refrigerator light bulb, is being pulled out of the noise by dishes in 3 deserts on opposite sides of the planet, and the data it is still sending back is forcing the publication of brand new peer-reviewed papers arguing about what is really out there. This is not a quiet, finished mission being gently wound down. This is a live scientific investigation at the edge of human reach. If stories like this are why you come here, subscribe now, because we are just getting started, and the next few years are going to be some of the most scientifically productive years this mission has ever seen. As Solar Cycle 25 ramps up, the next round of compressions from the Sun will start hitting the heliopause, and the post-hump debate is going to get direct new evidence to settle it. Meanwhile, the Big Bang is going to be tested, and the successor mission IMAP is going to keep feeding new data into the same models. There is a real, active, ongoing story happening right now at the edge of the solar system. And we are watching it unfold, one paper at a time. So let us bring this back to what it actually means. When Voyager 1 launched in 1977, it was built to last 4 years. It was supposed to visit Jupiter and Saturn and then go silent. Nobody back then imagined that in 2026, the same spacecraft with the same wiring, the same antennas, the same plutonium, would still be sending back measurements from a place no physics textbook had ever described. And the data is not just confirming what we already knew, it is contradicting what we thought we knew. The interstellar medium was supposed to be quiet. It is not. The heliopause was supposed to be a clean boundary. It is not. The Sun was supposed to stop shaping the medium right at the edge of its bubble. It does not. And right now, in 2026, the scientists studying this region cannot fully agree on what Voyager 1 is currently measuring. That is not failure. That is how real science moves forward. There is something quietly profound about that. A small probe, built with 1970s technology, carrying a golden record with greetings in 55 languages and sounds from Earth, is still out there, still functioning, still telling us things we did not know. The universe it is moving through is more complicated, more dynamic, more alive than we let ourselves believe. And every new measurement is a quiet reminder that the cosmos is not finished teaching us. This is what we do here on Proof. We chase the hidden story underneath the headline, the story they aren't quite putting on the front page, the slow, careful, peer-reviewed kind of discovery that doesn't make the loudest noise but completely changes how we see our place in the universe. And right now, the most important real-time experiment in the history of space science is happening 25 billion kilometers from your screen, and almost nobody on Earth is talking about it. Tell me in the comments what you think is really going on out there. Are we looking at a contaminated slice of the interstellar medium shaped by our own sun? Or has Voyager 1 actually crossed into something genuinely new? Share this with someone who still looks up at the sky and wonders. And as always, thank you for exploring the hidden universe with Proof. Note on fact-checking transparency, I cross-checked competitor claims against NASA, APL, peer-reviewed sources before re-reporting. 2 corrections to flag. Your source said IMAP launched in 2024. The verified date is September 24th, 2025. Your source described the LECP as operated continuously for 49 years. That figure is accurate. Instrument activated 1977, powered off April 17th, 2026. Both 2026 Astrophysical Journal papers referenced, Fraternale, Pogorelov et al. And Park, Burlaga et al., are real and dated 2026.